Hey everyone, those of you who are taking the quiz on Monday, um, well, here's the video study guide for the quiz. What you'll see will look very much like this. Those of you who were going to take it Tuesday, I guess you guys are going to take it after the 4-day weekend, but still, take a look at this, make sure you know how to do all the things on here. So let's see, let's take a look at some problems. Fred's puppy weighs 20 pounds, Bob's puppy weighs 40 newtons. Which puppy weighs more? Well, in order to get a basis for comparison, we've got to get the same units. So what I'm going to do is I'm going to convert from 20 pounds into newtons. So we have 20 pounds. And I know that the conversion up here is 4.448 newtons per 1 pound. So the pounds divide out. I'm left with an answer in newtons. And let me make sure I multiply that correctly. Oh, let's see. I'm going to say 20 times 4.448 equals. So that's about 89 newtons. Okay, so this is Bob's puppy, and Fred's puppy, we really haven't converted the weight yet, but that's already in newtons. So it seems like Bob has the heavier puppy at 89 newtons. Let me move me here. Imagine that a spacecraft has been designed, built, and launched to explore the atmosphere of the planet Mars. To enter a circular orbit around Mars, the craft has to be slowed down. The spacecraft's reverse thrusters, its brakes, is supposed to deliver a force of 500 newtons whenever it's fired. The thrusters, however, actually deliver 500 pounds of force. Is this too weak or too strong, and why? Well, again, we need to either convert newtons to pounds or pounds to newtons. Since we just converted pounds to newtons up here, let's convert newtons to pounds. So if we have 500 newtons and we go up to our conversion here, and we know that there's 1 pound per 4.448 newtons, we can figure out what 500 newtons is in pounds. So let's see if I can find my calculator again. So let me move me. 500 divided by 4.448 is, oh, I must have hit times. 500 divided by 4.448 equals. So that is, no, that can't be right either. 500 divided by 4.448. What did it say? 44. That's strange. Clear. 500 divided by 4.448 equals. There we go. There's a number I can agree with. So that is about 112 pounds. And this compares with the 500 pounds. So we know that the 500 pounds is much greater. Okay, so we're comparing in similar units, and right away we can tell that the 500 pounds is much more than the 500 newtons. Okay, next problem. The acceleration due to gravity on the surface of the moon is 16% that of Earth. If a lunar rover has a mass of 1,000 kilograms on Earth, how much does it weigh on the moon? Well, let's see. So weight is mass times gravity. This is 1,000 kilograms mass, and the acceleration is about 1.6 newtons per kilogram. Kilograms divide out, that leaves me with 1,600 newtons. So that's what it weighs on the moon. If you wanted to find out what it weighed on the Earth, it would be something like 9,800 newtons, right? 1,000 kilograms times 9.8 newtons per kilogram. Okay, next problem. A 100 kilogram astronaut weighs 600 newtons on a different planet. What is the astronaut's mass on that planet? Let's see. Does the mass change? I hope everybody remembered this. The astronaut's mass on that planet, and in fact anywhere else in the universe, is still 100 kilograms, because mass is a fundamental measure, or a measure of the fundamental amount of matter in something. The amount of matter does not change. What is the acceleration due to gravity on that planet? Well, if weight is mass times gravity, and I'm just going to use my visual calculator here, and I would like to find G. That leaves me with weight divided by mass. So G is equal to weight over mass. The weight is 600 newtons. The mass is 100 kilograms, and that would be 6 newtons per kilogram. Okay, moving right along. A 115-pound woman sits on a 150-pound stool. That's a very heavy stool. With her feet above the floor. Is the woman in equilibrium? Well, the question to ask is she changing her motion? And if she isn't, she's in equilibrium. So I'm going to assume that she's at rest, and therefore, if I add up all the forces that act on her, I'm going to get a net force of 0, which means the acceleration or change in motion is also 0. And we call that equilibrium. Likely the stool, since it's wedged between her and the floor, is not changing its motion either, so we're going to say that is also in equilibrium. So I'm going to say both in equilibrium. What is the net force on the woman and on the stool? Well, if something is in equilibrium, the net force is equal to 0. Describe how to draw a free body diagram for the woman. Well, here's the woman. She's very, very tiny. Here is her weight. Here is the normal force of the stool pushing up on her. And finally, this is the answer to C, by the way. how strong is the normal force that the stool exerts upon the woman? Well, it's equal to her weight. Okay, I hope everybody understands that. A student places a 10-kilogram box on a level floor. What is the net force on the box? Assuming equilibrium, if we have equilibrium, net force is 0. If the student now presses directly down on the box with a force of 20 newtons, what is the net force on the box? Guess what? If it doesn't accelerate, it's still in equilibrium. And what is the normal force on the box? Well, F net equals 0 still. And what is the net force on the box? So let's see. Let's draw what we have here. So we know the net force is still 0. There's a normal force pushing up. There is a weight acting down. And there's also an applied force of you pushing down on the box. So if I wanted to, and I do, what I could do is, knowing that the net force is equal to 0, what I'm going to do is I'm going to add all the forces acting on the box. So normal force is up. That applied force of you pushing down is negative, so it's down. And of course the weight is also down. We now have an equation to solve for normal force. So the normal force is going to be equal to the applied force plus the weight, or 20 newtons plus, what was it, 10 kilograms? Let's say that the acceleration, well, okay, I could say 98. That would be fine. And so now we know the normal force is going to be equal to 118 newtons. Okay, so that's the force with which the floor has to push the box back in order to keep it in equilibrium. Okay, hope that made sense to everybody. And last but not least, the student pulls directly up on the box with a force of 50 newtons. What is the net force on the box? Okay, so let's see what changes here. Still an equilibrium problem. So let's see, I'm going to draw my free body diagram. So I have some normal force. I have a 50 Newton applied force. And I have the weight, which is of course mass times gravity. Okay, so the only thing that happened really is that my applied force changed size and direction. So if I add up all the forces, normal force is headed upward, applied force is headed upward, and weight is headed downward, as weight will always do. So there's our equation for something in equilibrium. I'm going to solve for normal force, and I get mg minus the applied force. I'm actually with my applied force, I'm actually helping to hold the box up, right? So if there was no applied force here, then the normal force would be equal to the weight. Over here, in the previous problem, the box had to actually push harder. The floor had to push the box harder because you were actually adding to the weight by pushing down with an extra 20 newtons down onto the box. Okay, so here the applied force goes the other way, and that actually takes some of the load off the floor. Okay, so 98 newtons minus 50 newtons is equal to 48 newtons. Okay. So, know what's meant by equilibrium. Know how to draw a simple free body diagram, something like this. Know that weight is mass times gravity. Know how to solve that three ways using the visual calculator. Right, if you're looking for gravity, it's weight over mass. If you're looking for weight, it's mass times gravity. And if you're looking for mass, it's weight over gravity. Also remember that mass remains constant no matter where you are. Your mass is constant everywhere in the universe. So if the acceleration due to gravity on the moon is 16% of that on Earth, if a lunar rover has a mass of 1,000 kilograms on the Earth, how much does it weigh on the moon? Weight is mass times gravity. The mass times the acceleration due to gravity is the weight. Okay, imagine a spacecraft has been designed, built, and launched to explore the atmosphere of the planet Mars. To enter the circular orbit around Mars, the craft has to be slowed down. The spacecraft's reverse thrusters, its brakes, BRAKES, is supposed to deliver a force of 500 newtons whenever it's fired. The thrusters, however, actually deliver 500 pounds. Oh boy. Is it too weak or too strong, and why? Whenever you have one of these comparison problems, you have to get both measures of force, or whatever it's a measure of, into the same units. So what I chose to do was I chose to get newtons in pounds and compare that to the 500 pounds. I found out that if the spacecraft fires with 500 pounds of force, it is much greater than anticipated, because 500 newtons of force would only be 112 pounds. Okay, that would be an unwelcome surprise, is my guess. And Fred's puppy weighs 20 pounds, Bob's puppy weighs 40 newtons. Which puppy weighs more? Well, again, you have to get them in the same units in order to have a basis for comparison. So I chose to convert pounds to newtons, and I used the conversion factor, knowing that 4.448 newtons is 1 pound. Pounds divide out, and you're left with 89 newtons. 89 newtons being the larger of the two numbers, which is the weight of... Oh, I'm sorry, that's actually Fred's puppy. Oops, wait a minute. Wait a minute. Okay, so if you guys have the assessment tomorrow, good luck, study hard, and we'll see you then.